The strangest thing I've ever seen at NASA wasn't a fireball in the sky or anything resembling a UFO. It was a small line in the Fitz header and a faint green spot on an old Hubble frame that, by all the laws of celestial mechanics, simply had no right to be there. If you've never worked with archives, you might find it hard to believe how frightening an ordinary astronomical file can become when it starts acting as if it's rewriting its own past. Officially, I work at MAST, the Mikulski Archive for Space Telescopes, home to data from Hubble, TESS, Kepler, and dozens of other missions. I'm not a space hero, not an asteroid hunter, but someone who spends 8 hours a day immersed in humanity's digital memory of the sky, meticulously ensuring that not a single byte is lost. When 3I/ATLAS was announced, the third interstellar object after Oumuamua and 2I/Borisov, we at the archive were also touched. NASA launched an unprecedented observing campaign, and one of the goals was simple: to check whether Atlas had accidentally entered Hubble's field of view long before its discovery. The idea was purely routine. The JPL Dynamics team sent us a back integration of the 3I/ATLAS orbit, a set of ephemerides showing where, according to current measurements, the comet should have been in previous years, when Hubble was already operating. Formally, this is meaningless. Its trajectory is hyperbolic, interstellar, and 20 years ago it was too far away, too dim to be seen. But sometimes you manage to catch so-called pre-discoveries, when an object accidentally appears in old frames. No one expected a miracle. We simply ran a cone search. Give me all Hubble frames in which this point on the sky falls within the field. The script ran for about 6 hours. The results list contained a predictable scattering of empty fields, deep surveys, random galaxies, calibration frames. I began opening them one by one, as usual, overlaying the 3I/ATLAS, predicted position on the image, empty again, and again. And then I opened one of the old WFPEC-2 frames, dated 2005, and saw that same spot. At first, I thought it was my imagination. At full field zoom, the image looked ordinary. A background of galaxies, stars with the familiar diffraction crosshairs, a few cosmic rays. But as soon as I zoomed in on the predicted position, a tiny green halo appeared in the dark sky, a nearly perfect circle with a barely noticeable brightness gradient toward the center. It wasn't a star. It lacked a precise PSF peak. It wasn't a galaxy. It was too symmetrical, lacking an elongated disk. It wasn't noise. The pixels changed smoothly, not in a checkerboard pattern. And the most disconcerting thing, the crosshairs indicating this is where 3I/ATLAS should be if you extend its orbit backward, lay almost exactly in the center of this halo. I automatically checked the title. Date, April 17th, 2005. Instrument, WFPC-2, filter F5, 55W. Target, random field near QSO J1305 plus 0521. No comets listed. The RA/DEC coordinates match the ephemeris calculations to within tenths of an arcsecond. My only doubt was, either we just caught an impossible pre-discovery of an interstellar comet, or our astrometry had gone seriously haywire. The first thing I did was what any normal person does when they see something odd in an image. I dug into the raw data. The archive contains both calibrated frames and the original raw files, with cosmic rays, unsubtracted dark current, all that digital garbage the scientific world usually doesn't show in press releases. I downloaded the raw file, opened it in a separate package, turned off all automatic contrast enhancements, and looked only at the numbers. The eagle was there, muddy but stable, about 3 sigma above the background. I ran the frame through the classic pipeline manually: bias, dark, flat, cosmic ray rejection, and astro alignment with Gaia stars. Any step could have altered the shape of the faint source if it were an artifact, but oddly enough, after careful manual processing, the halo only became clear, and when spectrally evaluated through a combination of F555W and F606W filters, it began to suspiciously resemble the very green component just observed in the coma of 3I/ATLAS, an increased contribution in the C2 and CN bands, characteristic of an active comet with rich carbon chemistry. Coincidence? I said out loud to the empty room, hoping my voice would help me believe it. I could have chalked it all up to random background noise. Who knows how many faint comets have passed through these fields over the decades of Hubble's operation. But when I sent the position to the orbital integrator and asked a colleague at JPL to check whether 3I/ATLAS could have been physically at this point in 2005, the answer was very simple. No, not at all. Backward integration around its current orbit would have sent it far beyond Neptune's orbit, to a distance where it would not only be invisible to Hubble, but would effectively still be in interstellar space, just approaching the Oort cloud. I asked for the orbit to be recalculated without all the recent refinements to the sun's mass, without the effects of planetary perturbations, without anything that could be turned off just to shift the trajectory closer to that pixel. The difference was within an arc minute, but never to the desired position. The line between where it would be and where I see it had never crossed in the past. We're used to discrepancies. Even the most precise orbits have errors. But this was something else. Not noise, but substitution. It was as if someone had carefully added something to the frame that shouldn't be there, and in such a way that it matched not the actual motion history but our idea of where it would be if the current orbit were extended backward. I started looking further. An automated search of the entire Hubble archive for cones along the Atlas trajectory yielded 4 more suspicious observations. ACS, WFC 3/UVIS, various years, 2009, 2012, 2017. Different scientific programs, unrelated topics, faint galaxies, faint quasars, deep field surveys. But every time I zoomed in on the comet's theoretical position, the same thing appeared in the center. A faint, slightly fuzzy green halo with a nearly identical brightness profile. Sometimes a little brighter, sometimes a little dimmer, but always within the range of what could be called the same object at different distances. If this were a real, regular, long-period cometary object, it would all look quite plausible. A comet on an elliptical orbit, approaching closer and further from the sun at different times and appearing in Hubble's images. But we knew 3. I/ATLAS wasn't like that. Its orbit is hyperbolic, its eccentricity is greater than unity, and its velocity at infinity is non-zero. It's a visitor, not a resident. It doesn't have a previous orbit around the sun to have been captured by Hubble 20 years ago. I tried to get technical. Perhaps there was an error in the coordinate system. The WCS markers could have been corrupted. The calibrations could have been recalculated so that the actual field position had shifted slightly. Then we supposedly adjusted these frames to the new catalogs. This sounded reasonable until I compared the positions of 10 bright stars with the modern Gaia catalog. The discrepancies were less than 1/10 of a pixel, and the green halo sat like a peg driven in. Exactly where our program said, this point is the predicted position of 3 I/ATLAS on this date, if we continue its path backward along the hyperbola. I usually call someone else at this point, just to make sure I'm not going crazy on my own. That day, I called Kim, our ACS instrument specialist. We were sitting in front of a large monitor, scrolling through old footage, and every time I turned on the orbital layer, she turned purple. "It can't be real," she repeated, but her voice was becoming less and less confident. "It just can't be. WFPC-2 was searched 10 times before being archived. If someone had damaged the window like that, we would have found it by now." "But we didn't change anything," I replied. "And this applies everywhere, not just to one instrument." Kim leaned closer to the screen, turned on false color, and increased the contrast. "You know what's the worst part?" she asked quietly. "That green glow, it's almost identical to what we're seeing in Atlas's spectra now. The high CO2 to H2O ratio, that nasty C2. It's like someone took her current signature and smeared it backwards in time." We were silent for a few minutes, listening to the hum of the air conditioner and the ticking of the small wall clock, which at NASA, by the way, is always synchronized with the atomic clock. At that moment, the thought that had only flickered in the back of my mind finally took shape in words. "What if these shots were different?" I asked, "earlier, before—" I didn't finish the sentence, but Kim understood. "Do you have old copies?" she asked. I nodded. I had a strange professional habit, one that my colleagues considered borderline paranoid. I like to keep offline copies of particularly important data sets on external drives, disconnected from the network. A few years ago, we were calibrating old WFPC-2 sensors and uploading entire collections of archived footage to separate servers. I stole a copy onto a large mechanical drive, just in case. Sometimes, just in case, turns out to be the key to pulling out a monster. We went into my office. I pulled out the heavy black disk I'd almost forgotten about, plugged it into my old work laptop, and started searching the catalog for the same observation IDs. A couple of minutes later, the same WFPC-2 field appeared on the screen, but it was a 10-year-old version, untouched by the latest archive updates. I opened the image, zoomed in on the same area of the sky, and turned on the same stretch. There was no green halo there. The background was clear, a few dim galaxies, some noise, a single bright cosmic ray cutting diagonally across the field. No circle in the center, no hint of a comet. I double-checked everything. The title, the date, the exposure, the filter. It was the same frame, just different pixels. "Wait," Kim leaned closer. "Maybe it's just a different stage of processing?" "No," I said. "It's a product of the science of that time. Look, even the keywords in the title are different. The CRC checksum too. We downloaded the current online version of the same observation ID from MAST and combined it with the offline version, subtracting pixels one by one. The difference image flashed on the screen. Only minor calibration differences remained as shadows, but in the center, where the green halo had been in the new version, a clear positive spot appeared. It was as if someone had taken the old frame and added this particular structure on top, carefully blending it into the noise structure so it was unobtrusive. If this were a human hack, it would be a genius hack. But who would waste resources replacing a few pixels in 10 old sky images accessible only to a select group of specialists? And most importantly, why bother replacing them to include an interstellar comet, which no one knew about at the time the images were taken? We retrieved more old disks and other calibration data. The pattern repeated itself. Every time we found a local offline copy of a field before a certain date, everything looked normal. The online archive showed the same observation ID, the same date, the same program, but in the center of the field, a faint nighttime signature of 3I/ATLAS's presence. When was the last time you synced this drive with the archive? Kim asked. In 2017, I replied, during that storage migration. After that, it just sat in a drawer. 3I/ATLAS opened in 2024. It turned out that somewhere between 2017 and today, someone or something rewrote part of the archive in such a way that 20-year-old footage suddenly began to contain a faint imprint of an object whose existence no one suspected at the time. We brought in data security committees, cryptographers, and system administrators. The first thing we did was check the changelog. Unfortunately, the FITS files in the archive were never intended to be unchangeable. Calibrations, bias/dark reshoots, geometry corrections, and WCS updates could all lead to legitimate file resavings. Checksums were recalculated, and no one was maintaining a history at the pixel level. All we had was the fact. Current versions differ from older offline copies precisely in narrow regions that coincide with 3I/ATLAS positions extended backwards. It's clear that the first officially announced scenario was trivial, a bug in the new calibration pipeline. Some coefficients related to background correction were supposedly producing spurious structures. We were forced to thoroughly check all the software. We updated every script, every module, every table. Everything matched. We could reproduce the new version of the frame, but only if we used the latest versions of all dependencies, including the latest astrometric corrections and an updated catalog of reference stars. With older versions of the libraries, this extraneous halo effect didn't occur. It was as if the very set of external truths, where the stars are, how the Earth rotates, how the atmosphere deflects light, were forcing our pipeline in its honest attempt to produce an optimal image to create this faint spot. It was as if adding 3I/ATLAS to our models necessitated a recalculation of the past, in which it had always been there. But the real shiver that ran down my spine wasn't at the moment of these conclusions, but later, when we decided to check whether only Hubble was affected. We contacted our colleagues at ESO and Subaru, asking them for old fields that overlapped ours in both time and coordinates. They also had an online archive, and somewhere in their basements were dusty tapes and disks with raw backups. The scenario repeated itself to a frightening degree. The current online data shows a faint green halo, located exactly at the coordinates where the backward extended atlas should be. Offline copies from 10 years ago show nothing. Difference images showed a smooth, neatly inserted structure that looked nothing like a matrix defect or an atmospheric correction artifact. At some point, talk of bugs began to sound absurd. If this is a bug, then it's a universal bug, occurring simultaneously in independent observatories on different continents using different telescopes and different software. A bug that magically always draws an object with the same spectrum and shape, described by modern 3I/ATLAS physics, and always at a point determined by our own ephemerides, extended to a place where it shouldn't exist. At one of the closed meetings, I allowed myself to say out loud an idea that had been swirling around in everyone's heads for a long time, but no one had dared to formulate it. What if it's not we, who are adjusting the past to fit the comet, but the comet itself that is adjusting our past to fit itself? The room fell silent for a moment. Someone grinned wryly, someone rolled their eyes. But no one, mind you, immediately said, "Nonsense." There was another detail that everyone tried not to notice. The first 3I/ATLAS radio observations, carried out by ALMA, revealed something strange. In the millimeter range, its tail not only emitted its own molecular lines, but also contained a complex spectrum suspiciously similar to Earth's overall noise. old TV broadcasts, fragments of probes, our own radio cacophony, distorted and re-emitted as if the comet were carrying a filtered, intelligently welded cast of our technosphere. At the time, this was considered a beautiful metaphor. The interstellar object, they said, had turned out to be the perfect receiver for our radio league. Now, looking at how carefully the archives were being changed, it was hard to shake the feeling that it was not only receiving and re-emitting noise, but also somehow using it to write over our observation history. We decided to test whether human intervention was possible. We set up real-time monitoring of some new Hubble observations. Once a day, the telescope's data was archived, quickly processed through rough processing, and then the entire heavy-duty pipeline was activated. This typically took hours. During this time between the raw and calibrated frames, when they had not yet been touched by the new catalogs, we decided to monitor them closely. The experiment was simple. We took one program, a deep field of galaxies far from the current position of 3I/ATLAS, but with its angular coordinates matching its future trajectory if extended further into the solar system. The raw images arrived and we checked them. No extraneous objects, just galaxies and noise. Then we manually ran two versions of the pipeline, one using old astrometric catalogs and an old set of timing corrections, the other using the latest updates including new ephemerids, which now include a line listing 3, I/ATLAS, as an object of interest. In the old version, the calibrated frame looked as expected. In the new version, when we superimposed the comet's predicted future position, the familiar green halo appeared in the center again. This meant that even in places the telescope had never looked before, simply adding Atlas to our models and ephemerids, the simple thought of, "this is the trajectory it will take," resulted in the final image being neatly filled with a faint presence. Not because the photons had flown from space specifically from it, but because everything on which our corrections were based, catalogs, timescales, geometry, seemed to already take it into account as part of their structure. And the strangest thing is, it didn't look like an obvious hack. There wasn't a single foreign byte in the code, no suspicious TCP connections, no power surge in the data center. Everything happened within the framework of our own optimization algorithms, which honestly tried to minimize errors, adjust the model to the observations, and create a better picture. They simply did this in a world where the unspoken presence of 3I/ATLAS is already baked into the source data, an invisible parameter. At some point, the discussion went far beyond, "let's fix the pipeline." People from the theory group started drawing some terrifying diagrams. "If you imagine Atlas isn't just a lump of ice and dust, but a process," said one of them, an elderly speaker with a voice that suggested too many sleepless nights, "then the easiest way to describe this process is as an attempt to fit itself into any coordinate system that starts talking about it. You create ephemerides, it appears in them retroactively. You update catalogs, it adjusts the positions of the stars toward a trajectory that suits it. You construct time, it slightly adjusts the phases so that its signals are synchronous with all your yesterdays and tomorrows." I shuddered. "So you're saying," I asked, "that everything we see, from the radio noise in the tail to the green halos in the archives, is the same mechanism?" "I'm just saying that it could be the same mechanism," he snapped, "and if so, the most dangerous thing isn't that it alters the physical past, but that it rewrites our description of the past. For a civilization like ours, the difference isn't that great." We checked the photographic plates. Old glass ones, the very same ones that 100 years ago had recorded the sky without any numbers at all. In the basement lay the originals of the Palomar survey, black boxes containing silver grains of stars. We took several plates that digital scans had labeled anomalous, where after digitization, a faint halo suddenly appeared in the center, reminiscent of an Atlas image that had somehow managed to end up in the 1950s. The scans showed a spot. The physical plates, under a microscope, under proper lighting, were clear. No comet, no spot. This confirmed my worst suspicion. The change wasn't occurring in the physical world, but strictly at the level of digital representations. The comet, no matter how it operated, signed only where reality passed through the filter of our computing technology, where light was converted into numbers, coordinates into strings, and time into lists of corrections. We tried to isolate ourselves. We created isolated test environments where there wasn't a single file mentioning 3I/ATLAS. We wrote simple software from scratch to process a single field, but the outside world didn't stop. New versions of time standards arrived from international services, new star catalogs from Gaia, new ephemerides from the MPC, and each of these external truths, directly or indirectly, took into account the existence of ATLAS. There was a moment I remember especially clearly. It was late evening, almost night. Half the lights in the archive building were already turned off. The corridors were empty. I was sitting alone, opening an old printout of a WFPC 2-frame from that very offline disk we thought was untouched. The paper, of course, doesn't change with catalog updates. The pixels here are frozen, just as they were. I lean closer, looking at the dark center of the field, where the green spot lives in the new version. The air trembles from the fans. The lamp above the table hums faintly. And for a split second, it seems to me that on the paper, in the very center, I see a faint, barely discernible circle. Not bright, not confident, but as if the memory of my vision is trying to complete what it has seen so many times on the screen. I blink, running my finger across the paper. Nothing, a blank background. But the thought that comes next is the most unpleasant of all. If the phenomenon we observe truly affects not matter but the perceptions of it, then the boundary between data and reality lies not in servers or code, but right inside our heads. We humans are tied to the same coordinates, the same maps, the same timelines. We live in the world we describe. And if the description quietly, without fanfare or flashes, changes so that a single green comet becomes part of our sky retroactively, then sooner or later we will cease to remember that things could once have been different. And then the question, was Atlas there 20 years ago, will cease to be meaningful. All our archives will say, yes, of course, see for yourself. All our models will say it was always part of this system according to these laws. All our telescopes will see the sky, where its trace runs through time, like a thread stitching fabric. Only rare, strange people will remain, with dusty offline disks in their bottom desk drawer, who will stubbornly repeat, I saw a frame where it wasn't there. And they will be told, it can't be. By all accounts, 3I/ATLAS was always there. There are things NASA never mentions in press releases, and they certainly won't mention that someone once proposed, at a closed meeting, to stop time. Not in the poetic sense, but in the most literal sense. To freeze the standard time, stop receiving any updates from international services, cut off our internal coordinate system from the outside world, like an infected network segment. The idea was born not out of paranoia, but out of desperation. We saw how everything that came into contact with Atlas, ephemeris, catalogs, calibrations, began to behave as if the comet had always been part of their previous versions. It was as if somewhere up there, a global repository was being quietly rewritten, and our local copies were then updating themselves with this truth during the next sync. So one of the theorists suggested, what if we stop synchronizing? What if we lock ourselves into our own local timescale, our own star catalog, and never update them with any external data? Normally this would have sounded like the ravings of a fanatic. In a room filled with printouts of difference frames, with a green halo and reports on the radio noise in the Atlas tail, it was perceived as one of the few testable scenarios. This is how the Zeroday Observatory was born. The idea was simple and terrifying. Build an observation chain that doesn't even see Atlas as an object, at least not at the metadata level. Take an old, pre-Gay star catalog, an old version of the time corrections, old software, set up an isolated telescope that's not connected to the network and see what the sky reveals. If we're right and all the contamination comes from updated descriptions of the world, not from physics, then Atlas shouldn't be able to retroactively add itself to these frames. The telescope chosen was small but sufficiently robust, one of the older 2-meter ground-based instruments decommissioned from the primary program but still fully functional. It was placed in a separate dome and placed in a silent mode. No permanent internet connection, only an internal closed network segment with a local server. Inside, they installed a system image compiled from archived versions of software dating back 15 years, predating all Gaia missions and the first mention of 3I/ATLAS in astronomical databases. A separate atomic clock was installed inside the dome, synchronized with the TAI once at the moment of launch. After that, it was intended to tick independently, without receiving any correction signals from the outside world. Our task was a simple exercise. Every night, point the telescope at the region of the sky where, according to modern ephemerides, Atlas should be located, but never allow online ephemerides to penetrate the system. The pointing coordinates were converted manually, using a chain of calculations the old way. Right ascension, declination, precession, nutation, atmospheric refraction, all from tables and thick paper reference books, not through automated services. It was like the kind of experiment astronomers in the 1970s might have conducted if they had known they were being threatened, not by a physical object, but by a digital ghost. The first nights were boring. The telescope was processing its programs. The server was writing raw footage to local storage, and we sat in the dark control room, listening to the clicking of relays and the hum of the dome's drive. The minutes ticked by on the quartz clock, and the atomic clock did the same, only without the large hands. The monitor showed the same background noise. Stars, galaxies, noise. But as the data accumulated, we began to notice subtleties. First, the absence. In areas where large observatories had long recorded Atlas's green halo, our images were pristine. Not a hint of cometary activity, even with aggressive contrast enhancement and stacking dozens of exposures. The sky looked as if Atlas hadn't even entered the instrument's coordinate system yet. Second, there were the discrepancies. When we compared the coordinates of bright stars in our canned catalog with their positions in the modern online Gaia, the differences were tiny but systematic. It seemed as if the entire celestial vault had been slightly, by fractions of an arcsecond, rotated around its center in the direction Atlas would have reached if its orbit had been extended further. If I didn't know what to look for, said one of our astrometrists, I'd think it was just another catalog update. A minor correction of the proper motions, and here we realized the most important thing. The world outside was already based on a new version of the truth, one in which Atlas was written into the past. Our small dome on the hill was perhaps the only place on the planet where the sky still remembered what it looked like before someone started rewriting observational history. The situation seemed almost reassuring. So what? Some said. We have a pure standard. As long as this telescope is alive, we have an anchor. This feeling lasted until the night when the atomic clock malfunctioned. It happened at 2:17 a.m. local time. The technician on duty was sitting at the counter when suddenly all his monitors flickered for a split second. They didn't shut down, they didn't reboot, but seemed to momentarily lose synchronization with something outside of them. Usually, such glitches are attributed to the network, the drivers, or the electrical system. But the network was independent, the drivers were old and proven, and the dome was powered by a separate line with a diesel generator backup. The technician, a meticulous man to the point of obsession, first looked at the main unit of the atomic clock. A small yellow relock indicator lit up on the front panel. This meant that the internal oscillator had somehow lost phase in the last second and was forced to reacquire it. This happened, very rarely, in the case of a strong electromagnetic pulse or mechanical shock, but the dome was quiet, no earthquake, no thunderstorm. The yellow light went out, and the numbers on the display continued scrolling. The technician logged the event, simply because that's what he was supposed to do. A couple of hours later, after his shift, he forgot about it. We remembered this 3 days later, when we began to compare the timestamps of the frames before and after this event. In the isolation dome, we synchronized all systems using the atomic clock signal. Every HJD frame, every JD value, every RA/DEC depended on the exact ticking of our local reference. If the clock had simply stopped, we would have noticed a discontinuity, but it didn't. It transitioned to a new state, slightly different from the previous one, so that no human eye could detect the difference. Usually, such transitions are a matter of adjustment, but when we plotted the difference between the old timeline, reconstructed from pre-event logs, and the new one, we saw that in a split second, our entire local TI had shifted forward by a tiny amount, and now matched exactly the official global TI, which we'd proudly ignored. It was as if someone had caught our isolated metronome by the flywheel and gently nudged it to tick in unison with the global one. We checked everything. Ferromagnetic disturbances, temperature spikes, localized noise, everything looked clean. From a physics perspective, it could have been just a rare internal hardware glitch. From our perspective, it looked like Atlas's first successful attempt to reach inside a closed system. Not through the network, not through directories, but through time. After that, the Zeroday Observatory ceased to be a consolation and became a control target. Every little detail was viewed as a potential symptom. Once a night, we compared our new frames with the previous ones, superimposed them, subtracted them, looking for something like that green halo. And one day, 2 weeks after the recapture of the watch, we found it. This didn't happen in the sky where Atlas should have been, according to modern ephemerides. It didn't happen where its actual hyperbolic orbit would have been. The spot appeared in a different region, in the control field we were observing to check the background. This field chosen at random was far from the ecliptic, from the galactic plane, from anything that even remotely resembled an interesting place. At the intersection of 20 nights, the new object was barely noticeable, at the noise level, according to the old method. But upon careful measurement, the brightness profile was familiar, soft, round, slightly elongated, which on the celestial sphere perfectly matched the continuation of 3 I/ATLAS's trajectory, if transferred not by physics, but by that strange digital logic that had already depicted the comet for us in old archives. We attempted to recalculate the coordinates using our canned catalog. The object didn't match any known star or galaxy. We tried to compare the same region with modern sky maps. Pan-STARRS, DES, Gaia. The object was already there. Weakly, but definitely. And worst of all, the metadata from the modern archive claimed it had always been there, at least since the first digital surveys. In our local archive, in the disk copies of this very field from 15 years ago, it was absent. While it was still possible to try to argue with Atlas, saying it was an interstellar comet, complex dynamics, model errors, there wasn't even that flimsy excuse here. We were watching the appearance of a new object in the sky, one that didn't obey any reasonable orbital history, but was neatly retroactively inscribed into all external databases except the single timeline we maintained in the dome. Someone on the night shift couldn't stand it and called it the Atlas Phantom, as if the comet were throwing out not just gas and dust but also tiny anchors of reality, filling the map of the sky with the very fact that we are mapping it. Meanwhile, ALMA continued its observations. In the millimeter range, the 3I/ATLA S-tail was behaving increasingly strangely. The spectrum, which had previously only revealed molecular lines and the faint but recognizable echo noise of Earth-based transmissions, now resembled something like a multi-layered recording over an old tape. In addition to old radio broadcasts, television signals, and mission voices, things that shouldn't have been there began to surface. Fragments of coded formats used in the satellite's onboard protocols, which hadn't even been output when the signal was supposedly recorded. It was as if the comet's tail had become a universal buffer, where humanity's entire technogenic memory of the cosmos was being rewritten. Every carrier wave, every probe ping, every ephemeris update was ultimately reflected there, broken down and returned to our receivers not as noise, but as a draft of a new version of reality. The more we tried to describe Atlas, the more it became part of the very structures with which we describe the universe. And it was then that someone finally said out loud what had been hanging in the air for a long time. Maybe we're not observing an interstellar comet. Maybe we're observing a protocol. This phrase seemed too computer-generated for astronomy, but upon reflection, it fit perfectly with what we had seen. 3. I/ATLAS in this scenario isn't just ice and dust, but the physical embodiment of the synchronization process. An object that enters any technosphere sensitive to the sky and begins carefully adjusting its maps, catalogs, timelines, and archives to some purpose as yet unknown to us. It is as if someone, much more ancient and advanced, leaves beacons in the universe, which upon approaching another civilization, do not so much collect data as rewrite its structure, making it compatible with something else. We like to say that we're recording the history of space. None of us were prepared for the fact that one day space would begin recording our history. Not on stone or ice, but directly in files, in numbers, in that thin layer between the world and our consciousness, where reality becomes data. And somewhere out there, in the tail of the green comet, millimeter waves continue to whisper our own signals back to us, only slightly modified, like lines of code in which an invisible parameter has been added between the equal sign and the number, the parameter that says, Atlas has always been here. And every time we click update catalogs or recalculate calibrations, we raise our hand and vote to accept that version. We tried to resist, of course. Not heroically, not in a Hollywood way, but in our own scientific way, through protocols, through hacks, through bypasses around what we ourselves had built. When you suspect that the very structure of data is infected, the first thought is to retreat into analog. Paper, film, pencil, mechanical chronometer, the good old sextant. We suddenly became romantic 18th century sailors, locked in white rooms with air conditioning and servers. At the Zeroday Observatory, we pulled an old photo wedge out of storage, a good, heavy one with a silver emulsion, and hung it at the telescope's focal point in place of the CCD sensor. It looked ridiculous, like trying to record a 4K broadcast with a slide projector. But that was the point. No electronics, no firmware, no emulation, no silent updates. Just light, glass, and chemistry. As we developed the first plates, I had only one question in my head. If Atlas truly works as a protocol, if its purpose is to replace the description of reality, then where does the line lie? At the byte level? At the signal level? At the level of consciousness? Could something that rewrites the Hubble archive and atomic clocks reach the photographic emulsion lying in the developer bath? The images showed nothing unusual. Just a diffuse field, a few faint galaxies, and a couple of stars with small diffraction spikes. No ATLAS, no green halo, no phantom spots. If it weren't for the date on the paper log, one might have thought these were taken in the 1990s. We sighed, just a little. And at that very moment, one of the young graduate students, who had never held a real photographic plate in his life, asked, "Where are the coordinates?" We were silent, because there were no coordinates. In the digital age, every image isn't just pixels, but also a trail of metadata. RA, DEC, time, reference system, and observation conditions. Here, we had a rectangle of light on the glass, and that's it. To turn it into a point in the sky, we had to measure the angular scale, tie it to reference stars, and fit it into a coordinate system that has long been embedded within those very same updated catalogs. We could contemplate the world, but we couldn't name it, couldn't say where it was. And this small detail suddenly turned the whole situation inside out. Atlas may not have touched the photons themselves. It didn't need to. It was enough to control the dictionary in which we record where and when. When we finally decided to link the plate to a modern catalog, doing exactly what we were trying to avoid, the result was both predictable and terrifying. The program, running on a separate machine, yes, we still had a computer, found the reference stars, calculated the transformation, and gave us the precise coordinates of the frame's center. Among them, neatly listed, as if it had always been there, was the line, Obj ID, Atlas Ghost Field, MAG, 23.1, type, extended. We never named this area that way. None of us created such a record, but in the directory we pulled from the remote server, this line existed, with a creation date long before our experiment began. And then, for the first time, I caught myself thinking something that had previously seemed blasphemous. What if this isn't a mistake? What if everything is going exactly as it should? It's just that the should in this equation isn't determined by man or nature. While we were tinkering with analog exercises, big astronomy was living its own, more frantic life. Alma continued to pluck fragments of our own broadcasts from the Atlas tail. Old TV broadcasts, Apollo communications, packets from Mars orbiters, digital noise from modern satellites. Some of these signals, when superimposed on real-time scales, revealed something that shouldn't have been there. Delays and advances incompatible with the speed of light. For example, a fragment of the rover's onboard signal recorded in the tail of ATLAS corresponded to a communication session that should have taken place 3 weeks after we discovered it. That is, the comet's spectrum already reflected a conversation that had not yet taken place. Of course it's a time error, the lab chief said, looking at the ceiling. A misinterpreted marker, a glitch in the logs. We've already been shown that our clocks can be nudged. But when 3 weeks later the rover actually sent out that very same telemetry packet, byte for byte, matching the Atlas echo, that special silence fell in the rooms, where the words of physics and the words of religion become surprisingly similar. It turned out that the comet not only rewrites the past, but also contains traces of future man-made noise in advance, as if the direction of time did not matter to it, and the entire human radio corona around the Earth was perceived as a single pattern stretched along its trajectory. If we were to try to describe it simply, we could say Atlas implements some kind of operator over our technogenic field. It takes everything we emit, past, present, future, mixes, filters, compresses, and returns it as a neatly structured spectrum. But we were far from being so dry. For us, this sounded like a death sentence. No matter what we do next, it's already accounted for in someone's protocol. At this point, those we had previously tried to keep at arm's length joined the story. People from cybersecurity, from intelligence, from strange departments where the walls are hung, not with pictures of nebulae, but with network diagrams and threat lists. Their question was direct and unpleasant. If Atlas can infect our maps and catalogs, could it impact global infrastructure, navigation protocols, financial system synchronization, communications networks? If the comet's millimeter wave echoes contain a modified version of everything we've ever sent into space, what's to stop something from using it as a code injection back into our network? We astronomers, accustomed to thinking in parsecs and billions of years, found ourselves for the first time discussing our Bode diagrams and cosmological models at the same meetings where we usually talk about cyber attacks and critical infrastructure. Someone proposed a radical solution. Completely shut down all space-based input systems, GPS, GLONASS, Galileo, telemetry, and deep space communications, while Atlas passes through the interior of the system. Revert to local clocks and paper maps like our Zeroday Observatory, only on a global scale. Someone else said quietly, late, and he was right, because even if we turned off all the antennas tomorrow, the protocol was already in progress. It was moving not only through cables and over-the-air channels, but also along that invisible boundary where data is transformed into decisions. We began to notice small things. Civilian aircraft navigation systems began to switch to backup algorithms more frequently, as if satellite signals occasionally contained incompatible corrections that the autopilots were rejecting. Synchronizing high-frequency exchange trading began to require increasingly frequent corrections. Words like anomalous desynchronization, rare bursts of time error, and GPS TAI inconsistency quietly appeared in reports. It was as if someone was carefully pressing on the fabric of reality from the outside, testing its resilience. Not breaking, not tearing, but simply exploring its limits. During this same era, something happened that I'm sure will never be recorded in the official chronicles, but which everyone who was there will remember. Several major observatories received incorrect answers from their own archives almost simultaneously. Astronomers working with long-term observation series like to perform so-called reverse queries. Take the current position of an object, roll back the ephemeris, and ask the database what we saw at those coordinates 10, 20, or 30 years ago. This is common practice. It's used to search for supernova precursors and early glimpses of active galaxies, and suddenly these queries started returning different answers for the same object, depending on which subsystem was asking the question and at what point. On Monday, you request a region of Atlas's future path and see only a blank background in the archive. On Thursday, without changing a single line of code, you repeat the same request and receive a 20-year-old frame with a pale green halo of unclear origin, neatly inscribed in the metadata. There's no evidence that the database was changed in the interim. No migration record, no update logs. As if Monday's answer was any less real than Thursday's, but at some point the very branch of history you were asking about was cut off and replaced with another. One of the programmers who worked with these systems said something that stuck in my head. We don't have a database, but a distributed version control system for reality, and someone with admin rights does a force push there. It sounded like a joke, but the more I thought about it, the less funny it was. Because in this analogy, Atlas acted not as an object of observation, but as a commit hook for everything we consider the observable universe. With every ephemeris recalculation, every catalog update, every instrument recalibration, it added its own little diff. Tiny, almost imperceptible, but adding up to a point where we'll one day look back and say, strange, Atlas seemed to have been with us forever. And here, somewhere between the SQL logs and the millimeter spectrum of a comet, I was overcome by a feeling I'd been avoiding for months. Perhaps we're already living in the version of reality for which all this was intended. Atlas may not be coming to us. It's passing through our history, leaving markers in the past, adjusting the present, and sucking up from the future everything we'd only just planned to send into space. What then does the phrase, "will approach to a distance of 1.798 astronomical units on December 19th, 2025 mean? Is it a geometric statement or part of a script we execute ourselves because we believe in our own ephemerides? I don't know. I only know that that night, when the latest update cycle rolled through the global catalogs, our Zeroday Observatory suddenly lost its name. On the old local server startup screen, where the words Zeroday Observatory had previously appeared. After the reboot, a different, neat, almost branded name appeared. Atlas Compatibility Node Number 1. No one changed the configuration files. No one touched the BIOS. But somewhere between the old Linux kernel and the ancient file system, someone added a line of text we didn't write. And as we stood there, staring at the green letters on the black background, the old atomic clock on the wall, the only artifact we still tried to trust, quietly clicked and moved its numbers forward 1 millisecond, bringing us closer to world time. Now it's a matter of faith. Do you believe we're still capable of separating natural processes from protocol? Do you believe Atlas is just a beautiful green comet and not a string of code that will one day stand at the beginning of all our equations? To be honest, I'm not sure anymore.